Still in Chapter 5. Nested loops. Forgive me while I adjust the projector. All right, just like other programming structures like if statements, things like that, you can nest them. You can put an if statement inside an if statement. You can put a loop inside a loop. In that case, there'll be an inner loop and an outer loop. And the inner loop has to repeat completely before the outer loop can iterate. Kind of like a clock, right? All the minutes have to go by before you can go to the next hour. So, something like this. No real reason to type it in, but if you were going to, write a clock that displayed, every 15-minute interval between 1 p.m. and 6 p.m., right, you'd need a for loop. Start at 1, keep going while it's less than 6, add 1 to it. Now, instead of calling it I could give it a better name, like hour, right? Hour is less than 6, hour plus plus, and then we need an inner loop. For int minute equals, we're going to start minutes as 0. We're going to take minutes up to 45. I guess just less than 60 would do. And each time we go, the minutes are going to increase. Here I am using single and plural. By 15 minutes each time. I guess I could have made y'all type this as well, but all right. And then, you'd print it out in here. So dot right line, right? You'd want to format it nicely, of course. I'm going to not format it nicely. For printing PM times. This is making me think of an assignment, by the way. Write a clock display that would print, all 24 hours of the day. And you could configure it whether to do military time or, traditional time. And if you're doing traditional time, it, would put AM or PM after it. Anyways, I'll think about that in the future. Okay, so clearly this loop begins and ends before the outer loop increments once, right? So hour starts off at 1, and then we count out, the minutes. 0, 15, 30, 45. Then we go back. Hour becomes 2, and so now it's 2 o'clock, and then we start over. We calculate the minutes, 0, 15, 30, 45, and so on. And so if we ran it, it would say something to the effect of 1: since I didn't format the time correctly, right? And so on. I'm obviously not going to type in all this time. So the outer loop just has to repeat. The inner loop has to execute all the way. So the loops never overlap, right? We never see the hour increasing independently of the minutes, right? It doesn't go from 1:30 to 2:45 to, 1:15 to 2:30 to 3:45 and then back down to 2, whatever. Oh, got an outer loop. If the outer loop condition is true, you have an inner while loop or do loop or for loop. And if that's true, it keeps running until it's finally done, and then it comes back up and it increments the outer loop again. So here they make a little an application kind of similar, right? But it's, of course, more complicated. Using an interest rate to iterate through all the values, If you do an interest rate of 5%, then it goes like that. If you do an interest rate of 6%, it goes like that. And then if you do an interest rate of 8%, you go like that. So there's going to be an outer loop and an inner loop. The outer loop will probably be controlling the interest rate because it keeps incrementing. And then inside the outer loop, there'll be an inner loop which increments the year. And then they did some cool stuff where, before the while loop, it looks like it's in another nested loop of some kind. To me, it looks like, why do I say that? I guess we could do it. Yeah, we could do this just with 2 loops. So accumulating totals. You know how to do accumulating totals. You've taken other programming classes, right? So you got to just declare your accumulator beforehand. You have to initialize it, or else it contains what's known as a garbage value. And some compilers won't let you use an uninitialized variable. C# is thankfully one of them. Java is another. Other languages like C, C++ will go ahead and let you use an uninitialized value. The compiler may give you a warning about it. And if that's the case, then if you use an uninitialized value, you just wind up with whatever happens to be in that memory location at the time. Because when the compiler creates a variable, it doesn't erase the memory that it was pointing to. So, whatever data was left in memory beforehand. Now, nowadays, to some degree, the operating system kind of wipes out memory and stuff like that, but we could prove it if we loaded up C++, and declared some variables and printed them out without initializing them. And we'd see that they weren't necessarily zero, as we might wish. But in this language, they are. So garbage, an unknown value. The C# compiler helps prevent this. We have to put a starting value in. So C# will not use a garbage value. That's good. I don't think any compiler should let you use, uninitialized variables. So once you have your loop, once you declare your variable, you have some kind of loop, whatever it is, right? And then you have some kind of thing that you're adding to it each time, right? And then down here, after you're done with it, you can use, calculate the average or whatever. Use the sum, whatever fashion you want. Now, if you're calculating the sum, you would add some value to it each time. If you're just using a counter, you would just do a plus plus, right? So that it would count, each time. Right. So why don't we just go ahead and do this? We're going to make an iterator, int I is equal to 0. I should make a for loop. They're easy to use, right? If I'm going to write a for loop, then I can get rid of all that stuff. And for int I equals 0, I is less than 100, I plus plus. If I'm doing summation, I don't need to start it at 0, because if you add 0 to it, then it stays 0. All right, so we would add sum to the value of I, sum equals sum plus I, and we would increment our counter each time. And then when we're ready to use the sum, double average is equal to sum divided by counter, but that's going to round down to the nearest whole number. So I should cast one of these to a double, or I should have just declared the sum as a double. That may be the easiest way. Double. All right, there we go. Like that. And you might think, oh, I could just divide by 100, right? Since that's I is less than 100. Well, actually, this one would count from 1 to 99. And I made that mistake, not intentionally, but, if we typed in 100 there, it would not be correct. And what if we were adding by tens rather than ones? Then it'd be difficult to predict what the counter was. So that's why we could keep track of the counter that way, separately from the sum. Counter increases by 1 each time, the sum increases by the value. If we're writing some kind of test score, thing that's adding up a series of user input, we could still increment the counter by 1 each time, but we would add the test score that the user enters each time. Use prefix incrementing versus postfix incrementing. It doesn't really matter. Oh, improving loop performance. I accidentally went to the next topic. Make sure the loop avoids unnecessary operations. What would an unnecessary operation is? This is a very common thing that I've seen before, and it makes sense to students, and it's not the end of the world if you did it. But you could declare your average, right? And then you could calculate it every single time you were in the loop, right? Like that. And when you were done with it, the average would be correct. But unless you're printing running totals, you don't need to calculate the average every time. All you need to know is the sum and the counter. So it's better to put this below the loop rather than in it, because this does take some time for the computer to do. So you do want to reduce unnecessary statements. You don't want to put stuff in a loop that doesn't need to be in the loop unless you just flat out don't care about performance. So consider the order of evaluation for short circuit operators. I think I've given some lecture about that already, have I not? How you use short circuiting to speed up execution Have I not? It's okay to say I haven't.
I don't think you have for this class.
Okay, okay. So, the idea of short-circuiting is that if you have an or expression or an and expression, let me show you what I mean. My classic example, are you hungry and do you have money, right? If hungry equals true and you have money, money greater than 0, then go out to eat, right? Whatever's supposed to happen there. And you put this inside a loop, to represent, 300 days a year, or 365 days a year, right? For day equals 1 day is less than 365, whatever. Or what if this is repeating thousands of times to represent your entire life, whatever. This loop is going to repeat a million times in a row, so we want to optimize it as much as possible. The way we optimize it is we take advantage of short-circuiting. Short-circuiting is when the compiler or the execution of language decides that part of the evaluation would be skipped. So example, if hunger is even false, do we need to even check our money? No, we don't need to check our money if hunger is false because they both have to be true. So the language has decided that if this is false, and just about every language I've ever used does the same thing. If this is false, it does not even bother to check that. So if you were hungry only 1% of the time, and you had money 99% of the time, it'd be better to put the hungry evaluation first, because that's the one that's most rarely true. Because no, I just worded that wrong. Skip that thought, I'm going to do or. Same idea. If we're sick, or we are tired. I need to make sure that I worded the short-circuiting. My brain just flipped there. If sick is equal to true or tired is equal to true, we get to stay home. My classic examples of and or. If sick is true, we don't need to evaluate tired is equal to true. So you want to put whichever one is most common first. Right? Because if this evaluates to false, we have to do 2 checks. But if this evaluates to true, we only have to do 1 check. So let's say that we're always tired, right? 90% of the time, we are tired. But only 5% of the time, we are sick. Which one should we put first? Well, what we want to do is we want to rule this out as fast as possible, because we can skip this evaluation if this condition is true. So we would put the tired first, because 90% of the time we would only need 1 evaluation. If we put this one first, then we would need to do 2 evaluations 95% of the time, right? Because 5% of the time it would hit and we could skip it. 5% of the time we would have to do that one. So if 90% of the time we are tired, that's 1 evaluation. But if we are not tired, then that's 2 evaluations. I spelled that wrong. For this one, if 5% of the time we are sick, whenever that's true, we do 1 evaluation. And then the 95% of the time, I need to put the percentages here. You probably already have it. I probably don't even need to keep typing it. So 95% of the time we are not sick, and so we would have to do 2 evaluations. Figuring this out, which one should go first? Well, 95% of the time we are not sick. So that one's going to be rarely true. 90% of the time we are tired. So that one is true more often than not. So 90% of the time we would only have to do 1 evaluation if this check is first. So I would rewrite this. I would say if tired equals true or sick is equal to true. And if you're just doing 1 if statement, the optimization doesn't matter. if it's being repeated thousands or millions of times, then optimization does matter. And so, in general, for for loops, not for loops, for or, if the first operand evaluates to true, first operand is true, then the second one is skipped. So you put as the first operand the one that is true more often. And works the other way. And move this up here. Maybe I won't go through all that 95% of the stuff, but if we're doing and, I'm going to remove these. We got the idea that they're in loops. If we're doing and, if the first one is false, then we get to rule it out. So if 5% of the time hungry is true, then we have to do both checks. No, then we have to do both checks. It requires 2 evals. The other 95% of the time, then that's only 1 evaluation. We would rather code it so that as often as possible we only have to do 1 evaluation. So so hungry is equal to true would not be the right one to put first, because only 5%, because whenever it is true, it's only true 5% of the time, and so the vast majority of time we have to do 2 evaluations. 95% of the time. I think I worded that backwards. Let's write the short circuit definition. If using and, if the first operand is false, the second one isn't checked. So the first operand should be the one that is true least often. Whereas for, you want to put the one that is true most often first. Just have to kind of flip your logic. And so if we're hungry only 5% of the time, and we are tired 50% of the time, so that requires 2 evals. 50% of the time it's false, only requires 1 eval. Well, I want to put the one that's least true, least often true first, to take advantage of short circuiting. Well, this one's true least often, so I would put the hungry check first. Wait, not tired, money in this case. All right, hope that made sense. Read up on short circuiting if you need to get that idea. These statements that I've written, even though it took me a couple of times to get to it, are absolutely true. Just memorize those. For that, for and memorize these things for or. That's how to optimize loop performance. If you're really, really, really desperate to improve loop performance, you do what's unrolling the loop. And this is idiotic, but you could do this. Like if you're doing this, I is equal to 1 while I is less than or equal to 10. Print I, and I'm doing pretty much pseudocode. This is no longer C#, right? And then I++. If you were writing this in some kind of environment where speed was absolutely critical, you could do what's called unrolling the loop, which is this. I is equal to 1, print I++, print it again, 2, 3, 4, 5, 6, 7, 8, 9, 10. Why is that faster? Because this comparison takes an amount of time, right? It has to do memory access to pull up that I, that has to do, some time, spend some mathematical time doing that comparison. So by avoiding doing that comparison, if each one of these took a second, right, if that took a second, that took a second, and that took a second, and that took a second, well, this is 3 seconds that would need to be iterated 10 times. That's 30 seconds plus 1 for that is 31. But if we count these out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Only took 22 rather than 31 in order to do it like that. And we wouldn't even necessarily need to increment I the final time. And then it's 21 as opposed to 31. We got almost a 30%. We improved our performance almost by a third by unrolling the loop. You never want to unroll the loops unless you're absolutely in dire circumstances for performance time. And what if this loop needed to repeat it 10,000 times? Would you copy and paste that 10,000 times? No, you would not. So a loop should execute while x is less than the sum of two numbers, and that neither a nor b is altered in the loop body. This could be written as while x is less than a plus b, or we could do the sum is equal to a plus b while x is equal to sum, and then later on we probably, I guess we're going to be iterating I from now on. So although they don't show that down here, there would be inside the body some kind of incrementing for x. Same for this one. Some kind of incrementing for x here. So the code on the left, the loop executes 10,000 times, and a plus b is calculated, or excuse me, 1,000 times. And a plus b is calculated 1,000 times. We put some math in our evaluation. If we could skip putting the math inside the evaluation, and if we can skip putting it in the loop body, it'll execute faster, right? We calculate the sum, we calculate a plus b one time, and then we go into the loop and repeat it 10,000 times or whatever. You know, that way we're not having to repeat that. So, you know, if we were going to count the number of seconds it would take, because this is going to repeat 1,000 times, this check, this addition, well, the whole condition, the whole evaluation would take a second. That calculation would take another second. That would take another second, and then the loop body would take a fourth second. All right, so that would be 4,000 seconds if it repeated 1,000 times. But how about this? That's 1 second, but we're going to tuck that away. It's not part of the thing that's multiplied. That's a second, the loop body is a second, and obviously these are like nanoseconds instead. And that's a second, so we have 3,000. So this side only gets executed 3,001 time, you know, takes only 3,000 nanoseconds or whatever as opposed to 4,000. So don't put unnecessary operations inside the loop. We've already said that about like calculating the average, but it may be less obvious that if you put a math expression that has to be evaluated inside the while loop, then that's not good. Like what if it was a function call? Function calls take a while. Right? It's got to jump to a different part of memory, it's got to stuff some areas, it's got to create new variable space, and then when the function is done, it's got to release that variable space. So function calls take time. So if you could do the function calls before you enter the loop, rather than embed them in the condition here, you're better off. Yeah, this is considering the order of evaluation of short-circuiting operators. Loop fusion. If you have two loops that are executing over the same period of time, you can fuse them. That sounds, like I said, confusing. You can use loop fusion. And an example of that. What if you were going to calculate the minimum value of a series of numbers, and then you were going to calculate the maximum value of a series of numbers? Right, and so we don't know what the random numbers are. Maybe we're just calculating random numbers inside a loop. So maybe we do this for I is equal to 0, I is less than 199, so it's going to count 99 times because we're starting at 0, I plus plus, and then we generate, you know, okay, this is a bad example. But say whatever condition you have in here, while whatever, you're doing then if x is less than the max, then max becomes x, right? That kind of thing. We have a list of numbers we're processing. And then we're going to calculate the minimum. While whatever our condition is, if x is less than the minimum, then the minimum becomes x. And then we feel like calculating the sum of all them, right? So sum is equal to 0, and we have our while condition, whatever it is, and then we do sum plus equals x, whatever in there. Right, so we have 3 loops. They're clean, they make sense, they're easy to read, but we can improve performance dramatically if we use fusion, right? So we have our while condition, whatever it is. We do this check right here. And I'm sorry, but I'm going to shorten it like that so I can get as much space on the screen, text on the screen. Then we do the min check. And then we do the sum check. Or not, that's not even a check, right? Why do you do that? Because whatever this condition is, takes time to evaluate, right? And so we are performing 3 times as much evaluation, right? Because we're doing that check 3,000 times, and maybe we're incrementing a variable each time, and that would take time as well. So while x is less than 100, now would you calculate the max and minimum of a series from 1 to 100? No, you would really not. So this is just for examples. You would be parsing random numbers or going through, a list of values or whatever. But then you would need to reset all that stuff, and then the condition would still be while x is less than 100. And then you would reset the counter again, and then your while condition would be up to 100, and each time we need to add 1 to x. So we would need to add 1 to x there. We would need to add 1 to x there. And we would need to add 1 to x there. Maybe it's becoming clear that if all of that stuff was fused into one loop, we're only having to do this check 100 times rather than 300 times. We're only having to add 1 to x. We're only having to iterate x 100 times rather than 300 times. And I'm not going to do that thing about counting the number of nanoseconds. Just trust me on this one. This one would require approximately 3 times as long to execute as this one. Approximately. So we fused the loops. We did all the stuff that we needed to do together. Now, how many times are you going to get to do loop fusion? Well, I don't know. I think that almost comes intuitively, but when I demonstrate how to calculate the minimum and the maximum and the sum, I usually break them up into separate loops. Now I'm telling you not to break them up into separate loops. So, their example. We're doing x up to a certain number, and then we're calling method 1. Then we're doing the same exact thing for x up to 100, we're calling method 2. It's faster if you count, and then you call method 1 and you call method 2, if you can. Use prefix rather than postfix. I'd mention that to you. Plus plus x is marginally faster than x plus plus. And like I said, I wonder if compilers nowadays, smart compilers, fix that. Because it wouldn't take, well, I don't know how to write a compiler. I guess I should not say that. But anyways, you could write some code that would check to see how long something took. And this would actually be fun to enter. We could run this test. This is using something called a stopwatch. We can start our stopwatch, and then we can stop it, and then we can see how long it was running in milliseconds. That's kind of fun. I think we ought to do that. Launch Visual Studio and write something that uses a stopwatch. So as far as I know, this is lecture L, if you want to label it appropriately. I didn't label it appropriately. Oh well, I could change the name of program.cs to lecture.l.cs just by right-clicking on it, doing rename, and calling it lecture L with no spaces. Yeah, sure. Rename everything. Okay, so if we're going to use the stopwatch, we need to include some extra usings. I hope we can just do using up here rather than go and add a reference to it. Let's see if we can. So I'm going to add, well, that's interesting, using static system console. Anyways, system.diagnostics. Let's add that and see if that works for us. Using system.diagnostics. Oh, good, we didn't have to add a reference. That was good enough. So, what we're going to do next is we're going to create a couple of stopwatches. And yes, I'm looking at the notes here. I'm going to call them SW1 and SW2, just like they do. And how many times are we going to run each loop? Let's run them 100,000 times. So let's do int max loop equals 100,000. 1, 2, 3, 4, 5, 6. And by the way, if you're timing something like this, don't put print statements in it because print statements slow it down amazingly. If you write something that prints out 100,000 times, you're going to find that it takes a lot longer, and if you don't print anything out, it runs lickety-split. So anyways, that's going to be our max. Let's create two stopwatches. Stopwatch S1 is equal to stopwatch dot start new. Why don't we just create them separately? Right, stopwatch S1, comma S2. And then we'll do S1 is equal to stopwatch dot start new. And then let's do our loop. For int I is equal to 1, I is less than or equal to max loop. Let me zoom this in a little bit. I plus plus. This is the slower way. And then do something. I don't know what. Do they even have us doing anything in the loop? I'm afraid that if we don't have anything happening inside the loop, the compiler would optimize that out. Nope, they didn't have anything in there. Don't trust that. But I'm going to leave it alone. All right. Now we need to stop the watch. S1 dot stop. Now do the same thing, except just copy this code and change S1 to S2. And change the postfix notation to prefix notation. Put the I, the plus plus in front of the I rather than after it. And by the way, this is a common thing to do actually, to embed diagnostic information in here. So like you could find out that, you know, this bit of code is taking 15 seconds to run or whatever, while this one is taking 35 seconds or milliseconds or whatever. And there's other ways of doing that too. There are testing tools that you can use called profiling to figure out the longest part. But like if you're trying to measure a sorting algorithm, you want to run a bubble sort and you want to compare that to, you know, a selection sort. And so you could have that sort repeat, you know, 10,000 times. You could use a stopwatch to figure out how, you know, and then you could have the other sort run 10,000 times as well. And then you could compare, figure out which one was faster. All right, so we've got two stopwatches. We want to pull out the number of milliseconds out, which we do with dot elapsed dot total milliseconds. Those sound like they might be long. I'm not sure, but long el. Not liking that. Time 1 is equal to S1 dot elapsed dot milliseconds. And then do the same thing for time 2. Long time 2 is equal to S2 dot elapsed dot milliseconds. And for all I know, that returns an int rather than a long, but it doesn't hurt to put it in a long. Now let's print out our answers. CW tab tab. Love that. I++ takes placeholder 0 ms. And then put time 1 after the quote comma. Save yourself some time and just copy and paste that and make it ++I takes time 2. And let's add a read key to the bottom. Let's get a little bit more of the screen on here. They just put semicolons at the end of their fors rather than use open and close braces. Does the same thing, so I'm going to just put a semicolon there. Same way for this one. The only reason I'm doing this is so I can get more code on the screen at the same time so y'all can see what I did here. Alright, that's all my code. Hope it works. Alright, it took 0 milliseconds. And then the other one took 0 milliseconds. What's my suspicion? Either that we didn't run it often enough, or, for long enough, or that it's the loop is being optimized out of existence. So I'm going to run it 1,000,000 times. Alright, took 1 second. I'm going to run it 1,000,000,000 times. So that's a 1 followed by 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's taking too long. Alrighty. Running it 1,000,000,000 times, we saw that the prefix notation took 20 fewer milliseconds. Honestly, I don't think that's enough to really worry about. But what do I know? You know, a millisecond is 1,000th of a second, and it took 1,000,000,000 iterations to get it to show 1 millisecond. 20 milliseconds of difference. Which would mean it would take 50 million iterations to even show 1 single millisecond. But, sometimes time is of the essence. You're writing some, kind of laser device that's trying to shoot missiles out of the sky. That stuff needs to be as fast as possible so that it can track, the laser and fire it accurately. Then you would care. So just get in the habit of using prefix notation. Other programmers will admire. Oh, and by the way, if you're running on a slower computer than I am, then it might take a long time and just lower that 1,000,000,000. If you're running on a faster computer than mine, which is very likely, whatever. So looping issues in graphic user interface programs. Well, sometimes you don't even need loops because they're event driven, right? So if the user is going to click something and they're going to click it each time that they want to happen, you don't have to put that click inside a loop. The user's doing it for you. So you can write an event-driven program so that the action continues as long as the user continues to do it. On the other hand, sometimes your program will start a counter in the background for whatever reason. Or it'll start a separate worker thread to go and do stuff, right? So if you've written a program that's going to, access the internet, then maybe it's going to start another thread to go out there and pull that data in from the internet, and then when it finally gets an answer, it's going to update your screen, right? In which case, that could be a loop. But if it's just being generated by what the user clicks, then maybe it's not a loop at all, right? Each time you click here, it only prints hello. You don't really need a loop here. But they, instead of making it do what I just said, they let you type in the number of times. And so inside that event handler, they put their loop. Obviously, that loop is not spanning more than one event. And here we go. Not that you can see this, but each time they click yes, I want to see my balance, it prints out a new balance. That's not a loop at all because it just responds to a single click. So, summary. We know what a while loop is. I'm not going to read the summary. A for loop. We pretty much know what a for loop is now. You specify the starting value, the test condition that controls loop entry, and then the expression that alters the loop control variable. And before we leave this chapter, I want to demonstrate the other syntax for a for loop. Pardon me while I pause. All right. So I want to demonstrate an array, and then I want to demonstrate the syntax for using a for loop to access it. Now that we're talking about arrays, but I don't mind mentioning things a little bit before the chapter that talks about it. I've said that before. So what is an array? Well, in Python it was called a list. Right? In Python you just did something like this. Well, you don't do it like that in this language. And the syntax is slightly different than you do it in Java. I apologize, not my fault. So we're going to make an array of strings. String, and I put that there, and I'm going to call it colors, is equal to, and I'm going to put some curly braces here, and I'm going to put some colors in here. Curly brace, quote red, end quote blue, end quote comma, green, and so on. That's really enough, huh? Now I want to print those out. There's more than one way to do it. You can do it by its index value, or you can do it with a loop, by a for each loop. So let's do it just by index value. There's 3 items here. That's index 0, that's index 1, and that's index 2. Hopefully you've learned in programming that if you have lists or arrays or whatever, you start counting at 0 rather than 1. So I'm going to use I for my index variable. For int I is equal to 0, I is less than 3. Now hard coding the length of the array is moronic, right? I ought to be able to do something like colors dot length, right? I plus plus. So that's colors dot length because that's the name of my array, and dot length is a property of it. In Java, it was dot length without a capital L, I believe. Sorry for the differences. All right, and then we just print that out, right? Console dot write line. Tell you what, we're going to do it slightly differently. Sorry to change gears on you. String S is equal to colors subscript I, and then just print out S. Console dot write line S, like that. Now there's a reason I did it like that, right? We could have just put colors subscript I right there, but we didn't. I'll show you why. So we could do it like this. For each parentheses string S in colors. And you've seen this syntax already if you took Python, except it didn't use the word each. Right? You just did for S in colors. Then console dot write line S. All right. Which one do you like better? I like this one better, right? I don't have to mess with an index. The syntax is cleaner. Took fewer lines of code to write. The for header was shorter. So I love for each statements. And you can use for each for things other than arrays. You can use them for more dynamic data structures like stacks and lists and things like that. So that's the for each statement. Java has a version of for each, but it doesn't have the word each in it. Just slightly different syntax. Same for Python. It's just as for rather than for each. I like that this language uses for each. It makes me happy. Alrighty. I'm not even sure that I want to do any more. What do I mean by that? I guess I'll go check to see what my short assignment for today was. But we may skip it, or we may. Anyways, let's go check. while I check, huh? Alright, so here was my short assignment for this stuff. Except we're on L, aren't we? My little note here says that this code was written as part of a WPF application. Put it in a console application, make the changes, and then make it work. Alright. So if we look at it, I really ought to just make this homework, but so what's the code supposed to do? It's supposed to be a while loop. Write a while loop that counts x up to I max. Well, I didn't say where x was supposed to start. I guess I specify here. So there's my code. I set x equal to 0. I would want you to write the while loop right there. And then we don't even need to modify anything else there. And in region 2, a for loop. Write a for loop that counts y up to y less than I max. So where are these things defined? Where's I max defined? We use try parse. So we're going to ask the user what they should have done. I mean, what number we want to count up to. And then we use a while loop to print those numbers. And then we use a for loop to print those numbers. I honestly don't know if we need to do this. We could. Would it take any time at all to do it? Nah, it wouldn't. All right, let's do it. So let's just do it up at the top, though. Let's tell them what we're about to do. Console.writeLine. We're going to do some loops. Then let's get the maximum value of the iterations that we're supposed to do, which is this text called IMAX. So we're going to need a variable called IMAX. It's going to be an int. Now let's read in a string, string s. Let's ask them what our maximum value is going to be. Console.writeLine. Max value for loops, question mark. And then s is equal to console.readLine. Then let's do a try parse. So we need a Boolean variable. Bool be okay is equal to int dot try parse. We're going to parse string s, and its result is out space IMAX. So let's make notes of what we're doing here. Use a while to count from 1 to IMAX. But first we better validate that we got some good input. So if be okay. Or how about let's print the error message first. So if not be okay, console.writeLine, you fool. That wasn't a number. And then else, right, then we're going to do our good stuff. So I'm going to move this comment down inside my else. Then I'm going to pause for a second to make sure that you get a chance to code in everything that I've got here. Now let me paste my little comment here. We're going to use a while loop to count from 1 to IMAX. All right, that's pretty easy. Int counter, int I is equal to 1, while the counter is less than or equal to IMAX. Let's print the counter, console dot right line. Heck, let's just make it right, so that we're printing all the numbers in the same line. But if they chose 10,000, that's going to look pretty weird, or whatever. So we're going to write out the value of the counter plus a space. Yeah, I could have used formatting. It doesn't know what IMAX is because I capitalized M in there and I did not here. So I have to correct that. This needs to be IMAX with a capital M. And I need an increment counter. But as we've learned, incrementing it first goes there. But as I've said, if you're ever displaying output, that it slows down the computer so much that the effects of optimizing it like that would be infinitesimal. Now let's use a for loop to do the same thing. I'm going to reset counter. No, I don't. I'm going to do that inside the for loop. For counter is equal to 1, counter less than or equal to IMAX, capital M, counter plus plus, or plus plus counter. And then just again, console.write. Oh, there's something I want to fix. I'll do it in a minute. Console.write, counter plus a space. But I need to put a right line here at the end of it, right? Because it's going to print 100 numbers or 1,000 numbers or 10 numbers, and then it's going to go to the next line. So I need to put a console.write line after the while loop, and I need to put another one of those after the for loop. Console.write line. And then similarly, console.write line. Alright, let's get that going. There were build errors. Let's not get it going. A local variable named S cannot be declared in this scope because it would give a different meaning to S. Okay, so I've declared S somewhere else. Wonder where. Okay, so I'm going to call this one S-max, right? Good enough. String S-max. And then S-max is equal to console.readline. And then try parse S-max. See, if you give good variable names rather than single letters, you don't run into that problem nearly as often. So I just changed this 3 times. That, and that to S-max. Alright. Max value for loops. I feel like doing 20 numbers. Alright. Seems to work. And then it does our other stuff. Prints out our, our array. And then it did some measurements to find out that it took a whole 2 milliseconds to run 1 billion times. Whew. Alright. Man, that's enough, I think. Maybe I have another region down here that we were supposed to do. A do loop. Oh, yeah, of course we got to do a do loop. Can't forget our do loops. So here's our loops as they exist right now. You need to take a gander at it, pause it, and then we're just going to do a do loop. So here we go. Use a do loop to count from 1 to IMAX. So we do have to reset counter. Counter is equal to 1. Do, open brace. You know what, I bet I can type do and then tab. Yeah, that's cool. But then it puts this thing down here. But anyways, while counter is less than or equal to IMAX. And then inside here, we need to write it out. Console.write counter plus, and then since it's not a for loop and not auto incrementing, we have to increment our counter. So console.write counter plus a space, just so they don't all run together. And then plus plus count. Okay. And then white line, which me being lazy, I'm just gonna copy, come down in here and paste. I'm gonna do some loops, max value, I wanna print out 15. Yeah, they all print out the same. Hopefully we know how to write those 3 loops down. Especially if you've taken other programming languages. The only new one for you would be a do loop if you're coming here from Python. But that ought to be pretty clear as well. Alrighty. Why don't we call this done? Let me check out and make sure that the class has got it going okay too. You can find this code in the daily notes. Never just copy and paste the code from the daily notes though. That's kind of lame. You won't learn anything by copying and pasting.